Thank you very much, and thanks everybody for being here and to the organizers for inviting me. I hope that this talk is a friendly introduction to Stacky curves and the theory of local to global principles. So please ask me questions. I don't promise I will answer them, but I will try to give you an idea. So my goal is to give you an idea of why I think about the Stacky curves and how I think about them, not define them for you. I hate the definition. Okay. Oops. And yeah, let me say that the research that I will be talking about is joint work with Chris Keys, Andrew Cobbin, Manami Roy, Soumya Sankar, and Yidi Wang. And this is this is a rendition of a Stacky curve made by Gemini, a cute Stacky curve I asked for. So we'll see. But before we start with the theory of Stacky curves, I just want to start with something that you looked at during this week if you were a student at the summer school, and it's quadratic forms. So let's see, what have you learned during this last week? I'm sure you all looked at this quadratic form. Can you find 3 positive integers? Oh, non-zero integers such that this is true. 2, 1, 1. Great. Thank you. 1, 2, 1. Sorry. But wait, did I get it right? Oh, yeah. 1, 2, 1. Yeah. Okay, so we can find a solution very easily. And then once we have a solution, we can scale it nicely, right? So we can scale it by any constant we want. And then we get infinitely many solutions for this equation over the integers. So x squared plus y squared equals 5z squared, we can solve really easily. And we have infinitely many solutions. So this is a great quadratic form. And we're going to call a solution primitive, a non-zero solution primitive, if the GCD of x, y, and z is 1. So we can always rescale and take common factors out, so we can ask for our solutions to be primitive like this. Okay, so we have solved this equation, this quadratic equation. Now we can look at another one. I have just changed a 5 for a 3, and now the question is the same. Can you find, oh no, this is not gonna work. Okay, well you think, can you find a solution for this equation? No. Well, you have 5 more seconds to think. Okay, hopefully this works. Yeah, so the answer is no. Thank you. And how do we prove that there are no solutions? We can look, we're looking for primitive solutions now. So we don't want all of the numbers to be divisible by the same number. And we can take congruences mod 3. If there was a solution, that would be a solution mod 3 too. So that makes us kill the term 3z squared. So now we need to solve x squared plus y squared mod 3. And that's really easy. I have a table of the possible values of x and y. And here we have x squared plus y squared. And then we notice that the only solution is this 0 that we have here. So that tells you that x and y both need to be divisible by 3. But then you have 3 squared. You can factor out a 3 squared from both x squared and y squared. And you only have 1 3 on the other side. So that means that 3 also needs to divide z. So 3 will divide all of the numbers. And that's impossible because we are asking for primitive solutions. So the answer is there is no primitive solution to this. Very similar equation, but we don't have it. Okay, and so in general, these equations define quadratic forms. So here I have written for you the definition of a quadratic form. It's just, I just consider it as a polynomial in as many variables as you want that is homogeneous of degree 2. Okay, so a couple examples of quadratic forms, xy, x squared plus y squared minus 3z squared, the one that we just looked at. And I put my favorite quadratic form here because it represents all positive numbers. So I like all positive integers. I like it a lot. So once we have this setup, we can ask the same question. So given a quadratic form, do you have a way of checking if there is a primitive solution of that quadratic form equal to 0? And this is well known, and this is known as the Haase-Minkowski theorem. So okay, we need to ask for the quadratic form to be non-degenerate, but the idea, and I'm restricting over integer coefficients, but of course this can be done more generally. So we say that there is a solution for the quadratic form equal to 0 over Q, if and only if there is a non-trivial solution over QP for all primes P and over R. Okay. If you haven't seen QP before, you can almost truly change QP for mod P with some, I don't know, don't kill me. But you can think mod P for every P with some other conditions for bad primes. Yeah, Haase-Minkowski tells us exactly when do we have global solutions, so global solutions over Q, if we have these local solutions over primes and over the real numbers. Great. So now that we know everything for quadratic forms, we can go one step further. That's it. Instead of taking quadratic forms, I'm taking coefficients cube. And now the question is, do we have an integral, a primitive integral solution for this equation? And this is an example cooked up by Selmer also. The answer is very striking. So let's try to do the same thing that we did for quadratic forms. So for quadratic forms, we were trying to look at solutions mod a prime and try to prove that they couldn't exist, or if they existed, we were happy. If they existed for all primes, we were happy, and there will be a solution. So we can try to do the same in this example. That means we need to check if there are solutions mod P and if there is a real solution. So let's just start with the real solution. That one is easy. We get to take third roots of anything we want. And we get, I've written for you one solution here. And then we start prime by prime, checking if there are solutions. So mod 2, if my arithmetic is correct, you get a solution. Mod 3, mod 5. And now my exercise for you is to prove that for primes greater than or equal to 7, greater than or equal to 7, there is also a non-zero solution. And if you give up with this problem, you can see Kit's notes. Where's Kit? I lost him. Okay, you can see Kit's notes on local to global principles, and there is a really cool proof of this fact that uses units mod P for any of these primes greater than or equal to 7. So once you have done the exercise, the claim is that there is a non-zero solution modulo P for all primes, and also over R. But it turns out that this equation has no primitive integral solution. And the idea of how you prove this is you can assume that a solution exists, and then check mod 9. And then you do a lot of cases, and then you realize that 3 needs to divide all of the coordinates. So the solution cannot be primitive. Same thing that we did with the quadratic form. There are just more things to check. And more ugly arithmetic. But yeah, so here is an example of something that has local solutions for all of the primes and the numbers, but doesn't have a global solution. And the difference between these two examples, this family of examples, so we have on the one hand we have quadratic forms, and quadratic forms give us zero curves, and this equation that I have here defines a genus Button curve. I'm not calling it an elliptic curve because it doesn't have a point, so it's a genus 1 curve that is very close to being an elliptic curve. It just needs to get a point at some point. Okay, so I don't want to talk too much about the genus, but if you have seen the theory of curves, you know that the genus is a non-zero, non-negative integer that describes something of the arithmetic of your curves. So they are integers, they are all greater than or equal to 0, and they tell us a lot about how curves behave. During this week, you have been studying elliptic curves that are the ones that lie here, and you have been studying quadratic forms that live here, and you have seen all of the things you can say just from knowing what the genus of a curve is. Okay, are there any questions before I move on to, yeah? Yeah. Yeah. It's just in this case, it's just the shape of the equation. It's telling us what the genus of the curve is. But all quadratic forms that in x, y, and z are going to live here, and yeah, there we go wild. Yeah, thank you for asking. Are there any more questions? Yeah. Yeah, so that's what we're getting at, right? That's a really good question. So the point of knowing that they are genus zero curves is that Hasse-Minkowski applies for them. So to check if you have a global solution, you need to prove that you have solutions for all p's and a real solution. And that sounds like an infinite, I'm making a finite problem an infinite problem, but it turns out that it is easier to prove in practice. Yeah, thank you for asking. Are there, yeah? Oh, yeah, also a really good question, and we're gonna get to that. To be a problem, these are all homogeneous polynomials. So if you are used to working with affine curves, for example, you can just forget about the z. And then you have a polynomial equation of x and y that defines a curve. And then we are just homogenizing it by multiplying by the z. That's a really good point, and it's going to come up. So thank you for asking. Please ask more questions. These are great. OK, so I don't want to get to too many definitions, but I just want to set some notation. So for me, a curve is going to be defined by a homogeneous polynomial. Ooh, I didn't write that. A homogeneous polynomial in f, x, y, and z. And I'm going to define everything over Q. A lot of the things that I'm going to talk about can be generalized to other fields, but I just want to focus on Q right now. A solution for that polynomial equal to 0 is going to be a point on that curve. And then I'm going to write a c of q, x of q, sorry about that. X of q as the set of solutions to that polynomial equal to 0 over the rationals. And I can just change the field to wherever I want for solutions defined over wherever you want to have them. And then what we are concerned about is this question of having a global point over Q. How does it connect to having local points over all QPs and over R? And that's the local to global principle. So a curve over Q satisfies the local to global principle if having a point over Q wait, did I get this right? No, I got the implication right? Because this one is always true. If you have a Q point, you just take it mod P, and you found yourself a point. Sorry, the local to global principle is if you have a point for all QPs and R, then you have a Q point. So sorry about that. That should be going back instead. Oops. Great. And we can ask the same question. If we don't like the rational numbers, we can ask the same question over the integers. And you will just change QP by ZP. And you can answer similar questions. Okay. So that's the local to global principle for us. And we saw let me not get ahead of myself. So to check if a curve satisfies the local to global principle, you need to check, are there local points for all P and R? And then also you need to check, are there global points, right? And one implies the other always. So this one is always true. And then the question is, what happens with the forward direction? And the answer should be the same. So a curve can satisfy the local to global principle if it has no points, or if it has a point overall all QP and also has a point over the rationals. So what we have, the results that we have collected are first Hasse-Mikulski, that now I have written more in terms of curves. So if you take a curve that is smooth, projective, geometrically integral, better known as a nice curve, this is actually a term. So if you take a nice curve of genus 0 over Q, think of an elliptic curve, of a quadratic form, then the curve satisfies the local to global principle, always. And we have seen this elliptic curve that does not satisfy the local to global principle, but here is another very striking result. It turns out that if you consider curves that look like z squared equals f of xy, then a positive proportion of those curves that have genus 1 do not satisfy the local to global principle. And this is a theorem from Bargava in 2013. So you can think of many, many genus 1 curves don't satisfy the local to global principle. So you have this dichotomy of genus 0, and then genus 1, it breaks, and from then on, it keeps breaking. Okay. So the genus 0 curves are very special in our case. But the question is, what happens in between? That's the question that I want to answer, thinking about Stacky curves. And in order to get there, don't let me get ahead of myself, I want us to look at another equation that we have here. So let's look at something that looks like a surface. So we have x squared minus plus 3y squared minus z cubed. So we are asking for primitive integral solutions for this. And now we're in trouble because we don't have a homogeneous polynomial. So if we wanted to come up with a projective variety defined by this equation, we will get a surface. So this equation does not define a curve, but a surface. And then the theory of surfaces is rich and beautiful, but I love curves, and I want to stay in the theory of curves. So I'm going to be stubborn and try to make this a curve so we can study it. It's kind of a psychological thing for me, I think. But what's going to save us is we're not looking for solutions, any solutions. We're looking for primitive integral solutions for this equation. And that primitive is going to really save us. So again, we're looking for primitive integral solutions. Let me define this polynomial f of xyz equal to the polynomial defining our equation. And we are used to thinking about solutions to this polynomial. That's classical algebraic geometry. You may think about spec of zxyz mod, the ideal generated by f of xyz. But for primitive solutions, I want to put somewhere here that resembles a curve. And the idea is to note that if we have a solution for this equation, let me call it x naught, y naught, z naught, then we can scale by any constant lambda that we can come up with. We can scale by taking lambda cube, and lambda square, right? If we rescale the equation, then we get a lambda to the 6 from this term, we get a lambda to the 6 to this term, and lambda to the 6. So now we are back to being able to take out powers of numbers. It's not the same power. We need to be a little bit careful, but we can still have an action on the solutions by constant lambda. Okay. So that implies that there is an action of GM on this scheme. So you're just taking the solutions to that polynomial, and then you are acting by constants like this. That's all I'm saying. And what you can do is consider the quotient of this scheme by the action. Okay? And I don't want to focus too much on the definition of the quotient stack. I just want us to look at a picture and convince ourselves and understand what the picture is trying to convey to us. So if you have any solution, so let me, if you have any x naught, y naught, and z naught, let me let me act on a solution by the lambdas with the appropriate weights. So we get lambda square, lambda cube, sorry. Lambda cube, lambda square. That's our, this is our rescaling. And if this is equal to x squared, y squared, z squared, so if lambda stabilizes the point, x naught, y naught, z naught, then you have that two things are true. So lambda cube needs to be equal to 1 because the x naughts need to be the same. And then lambda square needs to be equal to 1 too. And which number cube is equal to 1 and square is equal to 1, most of the time, these two things are true, which means that lambda equals 1, right? That's the only number that we have that can hold these two equalities. The only points that in which this argument breaks is when you consider these points in which z is 0. Because now you forget the x cube equal to 1. You only have lambda square equals to 1. Which means that you have something of order 3 at those points. So you have an extra stabilizer. If you take something whose square is 1, you get an extra stabilizer here. So these are my fatty points in the Stacky curves. And they are the points in which I have extra stabilizers. In this case, the stabilizers are by μ3. Okay. So the way in which I think about a Stacky curve is you have a normal algebraic curve. In this case, my curve is almost a P1. But then there are these two special points that have extra stabilizers by the action that we're defining. And that's how I want to think about a Stacky curve. Are there any questions? So they are almost algebraic curves, but not quite. Yeah? Yeah, we can talk about it later, but I'm just thinking about it as in algebraic, like in the algebraic geometry sense. So. Cool. Any other questions? Okay, so I want to kind of forget about my equation and just think about this picture in which I remember that I have this action, this weighted action by GM. And that gives us this curve, this Stacky curve that has a base of P1 and then 2 Stacky points in which something weird happens. And it turns out that positive primitive integral solutions to f of x, y, z equal to 0 are in correspondence with integral points on the Stacky curve. Why is that? It's because we are exactly taking the quotient by this action. So we are making sure that in each class we can take out all of the possible powers of common denominators. And then we get our integral points that we care about. So this is how we recover something like a curve. Now it's a Stacky curve, and then the points on this Stacky curve are going to tell us the primitive solutions for the original equations that we were thinking about. Yeah? Yeah. Yeah. I'm asking for the GCD of the coefficients to not be to be equal to 1. Yeah. Thank you for asking. Any more questions? Yeah. Oh, I'm talking about the multiplicative group. Yeah, I think that's all I wanted. And the action of this group is given by exactly that. Cool. Any more questions? Okay. So I will feel really bad if I didn't write for us the definition of a Stacky curve. So a Stacky curve is a smooth, proper, geometrically connected Deligne-Mumford stack of dimension 1 over any field that you want. Wait, I'm missing. That contains a dense open subscheme. But what I want us to think about is an algebraic curve, so the P1 that you have in the base, with finally many Stacky points that have extra stabilizers. So that's all I want us to think about. And then the amazing thing about these Stacky curves is that you can have things like the genus of this Stacky curve is 2/3. So if you're used to the normal thinking about projective varieties, projective curves, this is really weird. But in this world, we have genus, fractional genus, and these 2/3 just comes from an analogous of the Riemann-Hurwitz formula. We are taking the genus of P1, which is 0, and then the contributions from the extra stabilizers of the Stacky points. Great, so we have kind of defined the Stacky curves, and now we can try to look at a local to global principle for integral points on these curves. I should say that I'm going to start focusing on integral points on Stacky curves and not rational points, because for rational points, the story is kind of boring. It turns out that the rational points are described by the rational points on the coarse space of the Stacky curve. So there is not that much that we can say. But for integral points, we have seen that they count primitive solutions. They tell us about primitive solutions, which is a really interesting problem to look at. Okay, so for the local to global principle, let's look at the first amazing result. So if you take a Stacky curve over the integers of genus strictly less than 1/2, then Bhargava and Poonen in 2021 published a paper that tells you it must hold the local to global principle. So in one hand, we had 0, the quadratic forms of genus 0. They hold the local to global principle. And then you can move all the way up to less than 1/2, and the behavior is going to be the same. You're going to have the local to global principle for these curves. But they also prove that if you are at 1/2, there is at least one counterexample, one curve of genus 1/2 that does not hold the local to global principle. So that's the cut, exactly. And they actually produce a family of counterexamples, but I just wanted to write one of them for us here. So it is a Stacky curve coming from this quadratic form. It turns out that if you take a quotient, as we looked at, for that quadratic form, and then take a further quotient by an action of G2, then that quotient has genus 1/2. It has local points for all p and for and over R, but it does not have any integral point. So genus 1/2 is the cut. And this is where what I want to tell you about my research starts. So before I do that, do you have any questions? Yeah? I don't know. I mean, the point is, these Stacky points are not full points in my mind. So their contribution is, usually when you do Riemann-Hurwitz, you have a map from a curve to a curve, right? And then you look at the ramification of that map, and that tells you what the genus is. Here you're doing the same, but these points, these Stacky points are not full, I have these extra stabilizers, so they can contribute in fractions. I don't know. Yeah. And yeah, I think how people like thinking about it is, instead of thinking about the genus, about the Euler characteristic of these curves, and they are all orbifold. They come from orbifold, so maybe you come. Okay. Thank you. Yeah.
Can every positive rational number be a genus of a Stacky curve?
I think so.
Okay. And is 1/2 so this shows it's sharp, but are there other genera bigger than 1/2 where the local global principle always holds, or is this truly a cutoff?
It's a cutoff.
Okay.
Yeah, and in fact, I'm going to show you an infinite family of, well, I guess our curves have genus n-1 over n for n odd, and then anything can happen for those curves. Some of them hold the local to global principle, and some don't. So that's coming. But there was another question before yeah. Oh, great. Yes. Yes, but. Yeah. It has to be finite, but yeah. I think it needs, if you want a specific genus, I'm confused. I would want to say that you can do anything if you're willing to change the genus, but someone can tell me that's false. Yeah. I see Santi saying yes, so. Yeah.
Actually, is that the equation? Is there supposed to be a z in the equation?
Oh no, yeah, it's z squared minus that. Sorry.
It's z squared minus.
Yeah, thank you.
So, but then if you.
Oh, z cubed.
I'm just trying to understand the action.
Oh, the action. So we're taking one quotient first by the GM, and then we're taking a further quotient there. Oh, it's a good question.
Is it GM?
Yeah, it's GM. Yeah, it's me too. Yeah, it's me too. Sorry. Yeah, that's right. Okay, let me move on from that, and let me tell you about this infinite family. that we want to establish. So we want to do something similar to the ideas that Bhargava and Poonen used. So we're going to consider polynomials of the form x squared plus by squared minus cz to the n for n odd. So we saw that in this example, the fact that 2 and 3 were relatively prime was really important to conclude that lambda equals 1. Here, that's why we want any solid. You can do something different for any event, but we're just going to focus on this case. These are examples of generalized Fermat curves. So if you note, this is, I mean, if you take the quotient, if you take the coefficients out, you have a generalized Fermat curve of signature 2, 2n. And in this case, we're considering any coefficients b and c. And these were studied classically by Darmon and Granville. So they try to understand how these curves can have global points. And they focus on b congruent to 1 mod 4. But yeah, they have a lot of results about this. And actually, in the paper of Bhargava and Poonen, they use these results of Darmon and Granville to prove that the curves don't have global points, the curves that they come up with. Great. So we are going to follow the same definition as before. We are going to take the zeros of that polynomial, act with GM, and then take that quotient. So similar to the construction that we made before. And then by Riemann-Hurwitz for Stacky curves, the genus of these resulting curves is n minus 1 over n. So we are always lying on the interval that we care about between 1/2 and 1 and trying to figure out what happens there. So instead of writing the mess, I'm just going to remind you that these curves come from these generalized Fermat equations, and they live in the weighted projective space where the action of lambda has weights n, n, and 2. Same as the action of lambda had weights 3, 3, 2. We're just generalizing that. And we want to check when these curves hold the local to global principle. So what we want to do is we need to answer if these curves have p-adic points for all primes, and if they also have a real point. And the second question that we need to answer is if they have any global point. So if both answers are the same, then the curve is going to hold the local to global principle. Okay, so two questions we need to answer. Let me start with, are there local ZP points for all primes and real points? And in this case, the answer just has to do with Legendre symbols. It's not that hard to compute when this happens, and I just want to give you an example in which we can conclude that they do have points. So if you, for example, take the Stacky curve corresponding to the polynomial x squared plus 29y squared equals 3z cubed, then the idea is you want to take x squared plus 29y squared and realize that that's a norm of that's the norm of an ideal in Q of a square root of minus 29. So on the other hand, you have a 3. So you're trying to figure out what's the behavior of 3 in that number field. 3 is split in the number field. So you know that there exists x and y such that x squared plus 29y squared equals 0. And that gives you a non-trivial p-adic point, triadic point on this curve. Great. So that's local points. And then the more interesting question is what happens when you're looking for global points. So same curve, and now we're asking, is there an integral point on this curve? And this is the theorem in collaboration with, let's see, yeah, Chris Keys, Andrew Coben, wait, yeah, wait, oh, Chris Keys, Andrew Coben, Manami Roy, Soumya Sankaran, Idewang. We write B as, we take all of the squares out from B, so we write it as f squared times a non-square B, B naught. And we consider the number field Q adjoin the square root of minus B naught with ring of integers OK. So for the purposes of this talk, I'm assuming that C and F are coprime, but we have a more general result. It just has more notation that I don't want to worry too much about. So there exists a localization, Rk, of the ring of integers of Rk, such that the following are equivalent. So the first condition is telling us when you have global points. We're asking for an extra condition for these global points, but it turns out we can always restrict to this extra condition. So that's the first one, the one that we care about answering. And there are two ways that you have to answer this question. The first one is there exists an element in the quotient of the units of Rk mod the end powers of units of Rk. And I'm not going to define what admissible is, but we just produce certain conditions for these elements of Rk to call them admissible, talking about valuations at different primes. And then the other condition is that your ideal generated by C in OK factors in a really nice way. So it factors as the product of prime ideals in which, on ideals that are supported at split, ramified, and inert primes, respectively. And then, moreover, we have a condition of what happens with the ideal supported at the inert primes. We are asking for this ideal intersected with a suborder of the ring of integers to be in an end power in the class group. Yeah. It doesn't. Oh. Support is inert. Am I doing it wrong? Oh, it's J. It's J. Yeah. Sorry, it's split. Yeah, J and I are the same. Yeah. Sorry. Yeah. It's split primes. Okay. So I don't want to talk much about this term or the proof, but this just gives us a condition in terms of class groups of suborders of quadratic number fields, or in terms of units in a localization of an order. And those are things that are easier to compute than checking if an equation has a zero. So we have some code that checks these two conditions in certain cases, and it allows us to prove if a curve satisfies the local to global principle in this family. And let me give you an example of how it works, how the admissibility part works. We have the same example as we had before, the 29 and 3. And you can try to brute force asking if there are solutions, if there are integral solutions. And you always find that the integral solutions are not primitive. So this suggests that the Stacky curve does not have an integral point. And in order to prove that, let me see, I have 2 minutes. So we end up noticing that the localization that we need to consider here is the ring of integers inverting the primes 2 and 3. And then the admissibility condition in this case, I just want to show you how it looks like, is valuations at the primes 2 and 3 need to be certain things. So the valuations of these D's need to be plus or minus 1 mod 3, or this should be the conjugate of P3. So we have specific conditions on what the valuations of these numbers should be. And then when you look at this quotient and you check all possibilities, I mean, this is a finite set, and you check all of the possibilities, you realize that there is no D that holds all of those properties. So that tells you that there are no integral points on the curve, which is what we will see, what we saw looking in a brute force way for integral points. And the thing that I want to finish with is, if you ask for proportions of how many rational points, how many curves satisfy the local to global principle in this family, our theorem gives you a way of computing these proportions in a nice way. So let me just focus on the punchline of the theorem. And the punchline is that there is a positive proportion of curves in the family with exponent 3 that non-vacuously satisfy the local to global principle, which means that they have a point, and and they have a point locally and they have a point globally. So that's our conclusion, and I think that's it. Thank you for listening.